All right, welcome back to CS50. This is the end of week 5, and this is one of my favorite problem sets that's on the horizon here. So if some of you have kind of been staring at this, trying to figure out what it is, letting your eyes zone in and zone out, odds are you didn't quite decipher it. But if you had, say from childhood, one of these pieces of plastic that came, for instance, with one of these cereal top boxes, and you held it up to this thing, what you would see, as did last year's students when they implemented this idea in code, was that it was Professor Plum in the lounge with the candlestick with this particular murder mystery. And so on the horizon for you this year is going to be a little someone different and a little someplace different with a little something different. But this is a teaser for problem set 5, whose focus will be forensics and the recovery of information that's either been accidentally or deliberately lost. I went through my inbox to retrieve an email from one of your predecessors. I'll keep it anonymous, but this was really quite fun to read since he sent this to us a few months after CS50 ended a year ago. And he wrote us, "Yesterday, my sister accidentally formatted her camera's digital media card and lost a year's worth of memorable photos. Parenthetically, she unfortunately isn't the best at backing up her data. This reminded me of problem set 5, so I thought I would try to run her memory card through the recover.c program that I wrote all the way back in October. So after 4 hours of figuring out how to create a raw forensic image from the formatted memory card, I came across this page and was able to do the following. After tinkering around with some of the command line arguments, I managed to create the forensic image. I installed and configured the CS50 VirtualBox. I managed to run the forensic image through my program and recover all 1,027 of my sister's photos. I find it absolutely amazing that I was able to go from being one of those less comfortable with no programming knowledge whatsoever to having the ability to recover data off of a formatted memory card in an actual real-life situation." So it does, in fact, happen. So this will be problem set 5. And now let's turn our attention back to this library. So very briefly, last time we looked at this function getString. We've been taking this taking this for granted for some time now. And underneath the hood, recall that it's actually been using some of these new fundamentals we looked at. This notion of memory management, dynamically allocating memory. And just as a quick review, so the function we introduced with which you can ask the operating system for memory is now called malloc, for memory allocation, and that memory ends up on stack or heap. So it ends up on the heap. And the intuitive explanation for that is that the stack memory constantly is coming and going. It's disappearing every time a function finishes executing. So it stands to reason that a function like getString, if you want whatever memory it's allocating to actually survive its return, which you do, otherwise what's the point in getting a string, that memory needs to go onto the heap. So henceforth, and we'll see this more in future p-sets, when you actually want memory dynamically, in other words, you don't know how much you need in advance, and that's absolutely the case when you have no idea what the human's going to type until he or she does. Or if you want to dynamically grow or shrink something, you're not just going to declare local variables anymore. We're going to start using a function called malloc. And it comes with an opposite function called free, which is a function we'll start to need to call when you want to tell the operating system, I am done with this memory. In fact, a little dirty secret of the CS50 library is that currently it leaks memory, whereby every time you call getString, we call that function malloc, asking the OS for memory, asking the OS for memory. But never once, probably, for your problem sets, and even in lecture, have we said to the operating system, I'm done with this string. You can have these bytes back. And so that's actually a bug. It's a bug that's been in the CS50 library from the beginning of the semester, but it's meant to simplify the process so that we can just assume that we're getting a string. But now, as we begin to dismantle these training wheels, anytime we actually ask the OS for memory, we're going to need to give it back. And so we're going to stop using the getString function, since now we can appreciate perhaps that it's not quite doing us a huge number of favors. Now, just as an aside, what do we care about memory leaks for? Well, if you've ever been running your Mac or PC or Ubuntu computer or whatever you have, and you find that over time it's getting slower and slower, and you're opening things like GChat or your browser or Photoshop or whatever programs you typically run, and you've been doing this a lot, loading things into memory, quitting loading. Well, if any of those programs has one of these things called a memory leak, where some programmer just screwed up and asked the OS for memory, but didn't necessarily hand it back, what can happen in real terms is that your computer can slow down, because your OS is going to think that it's out of RAM. And so future programs are going to use something called virtual memory, which for today's purposes is slower. So if you're ever finding that your computer's inexplicably getting slower and slower and slower, it might just be, frankly, that you need to reboot because there's some buggy program or programs that haven't quite been playing nicely inside of your laptop. So let's take a quick look at the CS50 library. This is cs50.c. We started looking at this last time, and it's OK if you don't quite understand all of the intricacies of getString, but a function that is a little easier is something called getInt. And it turns out that getLong, getLong, they're all pretty much equivalently implemented just for different data types. And they all conveniently use getString. So let's assume for the moment that getString works and it allocates memory for us, and it ultimately hands us back a line of text that the user has typed in. So here is the implementation of getInt that we've used as far back as week 1 in problem set 1 in C. So I first have kind of a curious feature here. I am deliberately inducing an infinite loop. While true means do this forever. So hopefully somewhere in this loop I have a break statement or a return statement, something that's going to deliberately break me out of this infinite loop. So let's see what I'm trying to do potentially infinitely. So I have in the inside of this loop, I'm going to try to get a line of text. So this is a familiar call. I'm now checking recall for line equals null. So as an example, when might getString return this special keyword null? Yeah, so if there was nothing typed in, and we can simulate that as we've discussed with Control-D, which normal humans aren't likely to type, but there's another scenario that could very well happen, and we'd get back null. If too long a string, right? If they paste in a huge essay that would fully exhaust the computer's RAM, getString, in as much as it calls malloc, might end up returning this special pointer value called null, which essentially means something bad happened. I don't know what necessarily, but I can't give you back a string. So we have to check for this. Otherwise, we risk later in our program those things called seg faults and core dumps. Now, why am I returning int max? Well, this is just a convention in C. There's kind of this problem fundamentally in C. Anytime you're implementing a function that's supposed to return a number, like an integer, because you can return upwards of 2 billion positive numbers, maybe as big as negative 2 billion. But if you want to return an error, you kind of have to arbitrarily say, OK, 0 represents an error. But then that's problematic, because if you want your function like getInt to be able to legitimately return a 0, if the user typed in 0, well, you can't use 0 as your special error value. So you can say, all right, let's use -1. If the user, if something goes wrong, we'll return -1 by default. But that too is problematic. What if the user wants to type in -1? So the convention that most functions in C adopt is they don't choose these popular values like -1, 0, and 1. They'll choose like 2 billion and 1, something that's crazy large and just shy of the maximum possible value. And we define that typically with a constant. So if we actually poked around a bunch of .h files in the appliance, we would see that someone had done sharp define int max, and it's something like 2 billion. And so we're kind of deciding, yes, we're sacrificing that number, but it's less likely to be useful than 0 or -1 or 2. So that's why we're returning int max just as a matter of convention. Now here's where things get interesting, and here's where the training wheels now come off. So this final chunk of code, this big branch here, is how getInt ultimately works. And it uses a function that you may have seen in readings or other examples called scanf, which means string scan formatted. So it's kind of like the opposite of printf. Printf obviously prints. Scanf reads in from the keyboard. So if we didn't have the CS50 library, you're seeing the hoops you would have needed to jump through in week 1 just to do something stupid like ask the user for a number. So how does this actually work? Well, notice first, just for temporary variables, I'm declaring an int n and a character c. And I ultimately want to put the number that the user types in into n. C, I just need to check if the user screws up. I need a character for the following reason. Here's the magical function. scanf takes a few arguments. The first argument is the line of text that the user typed in. So look at a string that the user typed in, and recall from above, we called getString, and we called the return value line. So that's all this is. This is literally the array of characters, aka string, that the user typed in. So we're saying to scanf, scan this string and try to extract an integer for us. But how do we do that? Well, much like printf, which is used for output, scanf does this for input. We say in quote marks %d, which is a placeholder saying try to fill this placeholder with an actual integer that the user typed in that's inside of this string called line. We have a white space character to the left and a white space character in the right, to the right, just to be friendly, so that if the user accidentally hits the space bar, then a number, that's OK. Or they hit a number and then the space bar, that's OK. We're going to forgive that. But we're not going to forgive typing any character other than a space. If the user types in 42 space F or G or any letter of the alphabet or symbol on the keyboard, what's going to happen is this. Scanf is also being told, all right, put the first number you see into this placeholder, but put the first character you see, alphabetical character, punctuation character that you see in what variable, apparently? In C. So this is just here as a bit of error detection. We only want to fill N. But just in case the user messes with us and we also happen to fill C, we want to be able to detect that the user typed not just a number, but also a number and a letter of some sort. So we have to tell scanf where to put those variables. And it is not correct, certainly, to do this. Because anytime you pass a variable into a function, how are you passing it? What's the jargon? So you're passing it by so-called value. You're passing a copy of it in. But if you want scanf to be able to fill those variables with some new values, how do you do that? Well, you have to write down that little scrap of paper, the visual we keep doing, where you have to say to scanf, put your answer on these 2 sheets of paper. So here is ampersand D, here is, or rather ampersand N, here is ampersand C. Put your int here, put your character here, because then I, the person who wrote this code, is going to check if scanf returns 1, that's perfect. The return value of scanf signifies how many pieces of paper that function filled with values. So if it only filled 1, the int called N, great, we're good to go. We can immediately free the line, the string that the user typed in, and that's new today, and then we immediately return that integer. But if the user somehow did not cooperate, did not just type a number like 42, and instead we get back from scanf the number 2, which signifies that they typed in some number plus some garbage character. Or if scanf returns 0 because they didn't type in anything somehow, the else condition is going to apply. We're still going to free that line, that string that we got from the user, and then we're going to nag them, retry, retry, retry. So if you've ever kind of wondered how that retry is being spit out automatically for you if the user doesn't cooperate, it's right there. Every one of these functions, get int, get float, get double, has that retry line. And if you don't get there, but instead the user cooperates, you instead return the int or the float or the double or the like. So those are the training wheels that are henceforth off. Questions?